Welcome to the Part B lecture of Advanced Mechanics of Solids, comprising the derivations from Part B, in which we are discussing equilibrium equations in polar coordinate system, including axisymmetry and derivations of thick cylinder, otherwise called Lami's problem, and also the derivation of rotating discs. We were actually planning to do some more lectures, but due to this constrained time schedule, we are planning to wind up with this lecture. We hope we have matched your expectations and your skill levels, and our videos have turned up to be pretty useful to all of you. Prepare well, wish you all success for the examination, manage your time efficiently. Once again, wishing you all the best. Now let's move on to the lecture. So far we were discussing with the rectangular coordinate system, that is XYZ coordinate system. So now we shall learn cylindrical coordinate system or polar coordinate system. So, as in the rectangular coordinate system, the coordinates were x, y and z. So, here in the cylindrical or polar coordinate system, we have r, theta and z instead of x, y, z. So, let us see how r, theta, z contributes to a cylindrical coordinate system. Now, let us assume I have a point here. Now, I have to draw a cylinder. So, for drawing a cylinder, from this point, I need a radius r. So, I am moving from this point to this radius r. Now, to get a circle, I have to rotate 360 degrees about this point. So, then I get a circle. So, now I have a circle. Now, for completing the cylinder, I have to project this circle either upwards or downwards or towards both sides. So, the coordinates r, theta and z contributes to the construction of this cylinder. So, this is how these three coordinates are used for building up a cylindrical coordinate system. Now, let us see the stress matrix T. So, instead of x, y and z, we have r, theta, z. So, this is the stress matrix. The first row represents the stress components in the r plane. The second row represents the stress components in the theta plane. The third row represents the stress components in the z plane. So, we have sigma rr, tau r theta, tau r z, tau theta r, sigma theta theta, tau theta z, tau z r, tau z theta and sigma z z. So, if you are having some confusion to write down this matrix, you can just write x, y, z here, and similar to this components of a stress matrix in a rectangular coordinate system, you can replace the variables accordingly, the same variables will come. So, instead of x, y, we have r theta. Instead of x, x, we have r, r. Instead of z, z, we have sigma z, z. Now, let us discuss the equilibrium equations in r, theta, z coordinate system or polar coordinate system. So, in the previous university question paper, it was asked to derive the equations of axisymmetric problem. So, axisymmetry is a special case of the cylindrical coordinate system. So, due to time constraint, what we are doing is we are deriving the equilibrium equations in r, theta, z system, and we are imposing the conditions of axisymmetry to obtain. So, axisymmetry is a similar principle, but for the time being, let us not learn in a different way. Let us derive the equilibrium equation in r, theta, z system and impose the conditions of axisymmetry to obtain the axisymmetric equations. Now, let us take a cylindrical element as shown in the figure of dimensions dr, d theta and dz. Now, this cylindrical element, you can assume if you just break a mosquito coil, you will get a small element that represents a cylindrical element. Now, this cylindrical element is of the angle d theta and height dz and radius dr. Now, this has got three planes. What are the planes? R plane, theta plane and z plane. Now, what is R plane? R plane is the plane in which R axis is perpendicular. Now, you can see R axis is perpendicular to two planes. This is first plane and this is second plane. This goes like this. So, we have two R planes. One is this plane and another one is this plane. Now, what about the z planes? We have two z planes, that is z plane means z axis is perpendicular to that plane. So, this is one z plane in which z axis is perpendicular, and beneath this is another z plane in which z axis is perpendicular. So, we have two z planes. Now theta plane I have represented here in a different diagram, because if I mark here it will be congested. So if you can mark here, that's also well and fine. So in order to avoid the congestion, I am representing it in a different figure. So theta plane, this is the axis in which we are rotating. Sorry, not axis, this is the direction in which we are rotating. So this is the theta direction. So theta axis is perpendicular to the plane. So this plane and the plane behind this plane. So these two are the theta planes. Now let us look at how to mark the stress components in the given planes. We have two R planes here, one on the back side and another on the front side. There will be three stress components, one is sigma RR, another is tau RZ and another one is tau R theta. Remember, I am marking the stress components on the first R plane here, which is on the back side of the given R axis. So sigma RR, I am showing it in the opposite direction of the R axis. Now why I am showing this in the opposite direction? Now here let us mark all the stress components negative, that is especially the normal component negative. If the normal component is negative, the two shear components also will be in the negative direction. Now proportionally, we will be marking the components in the positive side on the front plane. So let us not mark it for the time being. Here I am marking the components in the negative direction, so that these two components will neutralize and will maintain the element in equilibrium. So I am marking the sigma RR in the negative direction. So my tau RZ, what does tau RZ mean? Tau in the R plane in the Z direction. So this is positive Z direction. So my tau RZ is in the negative direction. Why? Because sigma RR is in the negative direction. If normal stress is negative, the corresponding shear stresses also will be negative. Now let us look at tau R theta. Now this is my theta plane. So tau R theta is also negative because sigma RR is negative. So which theta direction is negative? So anti-clockwise direction is taken as positive. That means tau R theta is positive in this direction. So we have to mark negative direction. So my tau R theta is negative, that is in the clockwise direction. Now let us look at Z plane. So this is your positive Z axis. So positive Z axis here. So we have two Z planes, one Z plane here, another Z plane here. So let us mark the stress components on the back side of the Z plane. So that will be here. So as I have explained earlier, let us mark the stress components in the negative direction, because the positive direction will be marked on the front side of the plane. So my sigma ZZ, now sigma ZZ is my normal stress. So sigma ZZ is acting in the negative Z direction, because positive Z direction is upwards. So sigma ZZ acting negative. My tau ZR, tau ZR is positive in this direction. I have to mark tau ZR negative, so I am marking in this direction. My tau Z theta is also negative. My clockwise direction is negative, so I am marking tau Z theta in this direction. Now let us look at the theta plane. So theta plane, we have two planes. Now let us mark, now this is my theta axis. As I have told earlier, the positive theta direction is anti-clockwise, that is in this direction. So I am marking the stress components on the back side of the plane, that is here. So my sigma theta theta I am marking as negative, because the positive component will be marked on the front side here. So sigma theta theta acting negative here. My tau theta Z is negative coming downwards. Tau theta R is negative because R negative direction is towards this direction. So my tau theta R is acting in this direction. So we have marked all the stress components. Now let us analyze the area of each plane so that we can calculate the corresponding forces. Now let us look at the R plane. So plane ABCD. So plane ABCD is the plane in which I have marked the stress components. Now what is the area of this plane? My area of this plane is, you can see this dimension is dz, or this dimension is dz. Now what is the length of this element? I am considering an element of radius dr at a distance of r from the origin. So my distance from the origin towards this point is r. So r into d theta gives the arc length. R d theta is the value of this dimension into dz will give the area of this plane. So area is equal to r d theta into dz. My stress components are sigma rr, tau r theta and tau rz. They are acting in the negative direction, as I have explained earlier. Now let us look at the front side of the R plane, that is plane EFGH. We had marked the stress components on the back side of this plane. Now we are analyzing what are all the stress components on the front side of this R plane. So plane EFGH, now we are traveling by a small distance from this plane to this plane. So we are assuming that there will be an increment for the stress components. Now let us see what is that increment. So that increment will be therefore these three components. Now let us see what is the increment for sigma RR. The increment is dou by dou R of sigma RR dr. So that the total value will come to sigma RR plus dou by dou R sigma RR dr. So how does this come? That is, the stress component at this plane will be the sum up of the corresponding stress component on this plane plus incremental value. So we are adding sigma RR here plus dou by dou R. So how does this dou by dou R come? Dou by dou of which axis I am traveling? I am traveling in the R axis. So dou by dou R of which quantity I am taking? I am taking sigma RR. Now into how much distance I have travelled. Now from this plane to this plane I have travelled dr distance. So let us see this once again. The corresponding quantity plus dou by dou R, dou by dou of which axis I have travelled, into which element I am taking sigma RR times means multiplied by how much distance I have travelled from one plane to the next plane, that is dr distance I am travelling from this plane to this plane. So sigma RR plus dou by dou R sigma RR dr. Now we are taking the stress components in R plane only. Now let us see what is the value for tau R theta. Again tau R theta plus dou by dou R. Again I am travelling in the same axis, dou by dou R of which element? Tau R theta times dr. Again I have travelled distance dr only. So same principle for tau RZ plus dou by dou R tau RZ dr. So all these values are positive because here we have taken all the negative. Now here we are taking all the components as positive, so that the stress components in both the planes will contribute to the equilibrium of the system. Now let us see what is the area of this plane EFGH. Area is, now the distance from the origin to this point is R plus dr. So this is the distance R. Now this distance is dr. So R plus dr into d theta gives the dimension of this FG into dz. Dz is the dimension GH. So R plus dr into d theta into dz gives the area of this plane EFGH. Now let us analyze the set plane in which we have marked the stress components, that is plane BFGC. So in plane BFGC the stress components are sigma ZZ, tau ZR and tau Z theta. We have marked it as negative. Now let us analyze what is the area. So for area, now BF and CG the dimension is dr only. This is the radial dimension of the element dr. Now what about the dimension FG and BC? We have to get a mean dimension between BC and FG. So for that what we are doing is we are taking it as R plus dr divided by 2. Remember, we are not taking R plus dr whole divided by 2, we are just taking R plus dr by 2, that is to get the mean dimension. This is 0 to R and this is dr. So dr by 2 means it will be some mean length of BF. So R plus dr by 2 into d theta. So into d theta means we will get a mean arc length between these two elements. So R plus dr by 2 into d theta gives the dimension of a mean arc into dr, gives the area of the Z plane. Now let us analyze plane AEHD. So plane AEHD, that is the Z plane, that is a positive Z plane AEHD. So here as I have explained earlier, so there will be an incremental value. So sigma ZZ plus, let us analyze sigma ZZ. So when sigma ZZ reaches here, sigma ZZ plus dou by dou of, it is travelling in Z axis. So dou by dou of Z times which element we are taking, sigma ZZ times, that is multiplied by how much distance I am travelling, dz distance I am travelling from this plane to this plane. So similar methodology applies for tau Z theta and tau ZR. Let us analyze tau Z theta. Tau Z theta plus dou by dou of which axis I am travelling, Z axis, times which element, tau Z theta, times how much distance I am traveling? dz, because it is the same plane. I am just taking the positive plane. I am just traveling from negative plane to positive plane, that is I am traveling through dz alone. So, all these three stress components are positive. Now, the area of that plane, the same principle as I have explained for the set plane BFGC, r plus dr by 2 d theta dr, to get a dimension of a mean arc in between AD and EH. So, r plus dr by 2 into d theta into dr. Now, let us analyze the theta plane. So, theta plane, plane ABFC, ABFE. So, the stress components are sigma theta theta, tau theta r, tau theta z as negative. We have marked negative because positive direction is anti-clockwise direction. So, the plane on the front, the stress components on the front plane will be positive, stress components on this plane will be negative. So, what is the area? Area is, now this dimension is dr and this dimension is dz. So, area is dr dz. Now, what about the front plane, front theta plane? Again the same principle as I have applied earlier. Let us analyze sigma theta theta. So, sigma theta theta plus dou by dou of which axis I am traveling? Theta. So, dou by dou theta times which element? Sigma theta theta, multiplied by how much distance I am traveling? D theta distance I am traveling. So, similar methodology for tau theta r and tau theta z, all the stress components are positive. Now, what is the area of the front theta plane? It is the same. So, dz into dr, dz into dr. Now, I am trying to simplify the derivation. Actually, the theta plane keeps on changing. We are rotating from 0 to 360 degrees. So, the stress components in theta plane needs to be properly resolved before resolving the forces, that is sigma fr equal to 0, sigma f theta equal to 0, sigma fz equal to 0. Now, this is a bit complicated. So, in order to simplify the derivation, I am omitting this portion. So, for derivation, you need to just explain the cylindrical element and explain all the three planes, r plane, theta plane, z plane, and mark the stress components and explain the stress components as I have explained in the previous page. Now, I am omitting the portion. I am just telling that this is the actual procedure. Now, let us don't go for detailing this procedure. Now, you can explain all the stress components and finally you can write sigma fr equal to 0, that is the summation of forces in r direction is 0, summation of forces in z direction is equal to 0, summation of forces in theta direction is equal to 0, which will give you three equilibrium equations, that is one in r direction, another in z direction and another in theta direction. So, equilibrium equation in the r direction is dou by dou r sigma rr plus dou by dou z tau r z plus 1 by r dou by dou theta tau r theta plus sigma rr minus sigma theta theta by r plus br equal to 0. So, in most of the cases this body forces will be treated as 0. So, the remaining part equal to 0 is the equilibrium equation in r direction. So, there is an easy way to remember three terms of the equation. The fourth term you have to by heart. I will explain. Now, let us take the equilibrium equation in r direction. So, let us apply the derivatives in the respective elements. So, I am applying dou by dou r here, dou by dou theta here, dou by dou z here. I have written in the order r theta z. So, I am applying the derivative dou by dou r, dou by dou theta, dou by dou z. So, let us take the equilibrium equation in r direction. So, dou by dou r of sigma rr plus, now for the second element always, now for all the three directions, for the second element you have to multiply with a 1 by r. You will come to know while explaining the equilibrium equation in theta and z direction. Now, for tau r theta I am multiplying with a 1 by r. So, 1 by r dou by dou theta of tau r theta plus dou by dou z of tau r z plus dou by dou z of tau r z. Now, the fourth term you have to memorize, sigma rr minus sigma theta theta by r equal to 0. Now, let us take the equilibrium equation in theta direction. Now, this is the theta plane. So, let us apply in chronological order, dou by dou r of tau theta r, dou by, now this is the equilibrium equation in theta direction, dou by dou r tau theta r plus, again the second term I am multiplying with a 1 by r. So, 1 by r dou by dou theta of sigma theta theta plus dou by dou z of tau theta z, dou by dou z of tau theta z. Now, the fourth term you have to memorize 2 times tau r theta by r equal to 0. Now let us take the equilibrium equation in z direction. Let us analyze the components in z plane. I am applying dou by dou r here, 1 by r dou by dou theta here, dou by dou z here. Now this is my equation in z direction. So dou by dou r of tau zr, dou by dou r of tau zr, which is same as dou by dou r of tau rz, plus 1 by r dou by dou theta of tau z theta, 1 by r dou by dou theta of tau theta z or tau z theta, whichever way you can write, plus dou by dou z of sigma zz, plus fourth term you have to memorize tau rz by r equal to 0. Now this is the equilibrium equation in r direction. So how to understand? I have mentioned Br, that is body force in r direction. This is, I have mentioned Bz, that is body force in z direction. So this is the equilibrium equation in z direction, and this is the equilibrium equation in theta direction. So we have three equilibrium equations. Now once it was asked, just write down the equilibrium equations in polar coordinates for 2D system. So for 2D system, so which coordinate to be neglected, r, theta or z? So if you carefully look at a coin, a 1 rupee coin or so, from the center you have to go to the radius and you have to rotate 360 degrees. That is, you need r and theta to just draw a circle. Now for the cylinder, we are projecting it by z units or h units. So for at least drawing a circle, we need r and theta. So for polar equilibrium equations in 2D, we are neglecting the z axis and the corresponding components along z. So whichever stress components in the z direction, we should neglect and we should make it 0. So there won't be equilibrium equation along z axis. So equation 2 completely vanishes. So equation 1 and equation 3 only exist, and out of equation 1 and 3, we should give 0 value to the stress components along z direction. Now if you carefully analyze equation 1, you can see tau rz, this is acting in z direction, so this must be 0. So this term we are neglecting. So what is the equation? Dou by dou r sigma r plus 1 by r dou by dou theta to r theta plus sigma r minus sigma theta by r equal to 0. Now equation 2, as I said, it will completely vanish, and equation 3 we are giving 0 value to the stress components along z direction. So tau theta z goes to 0. So what will be the remaining equation? Dou by dou r to r theta plus 1 by r dou by dou theta sigma theta theta plus 2 times tau r theta by r equal to 0. So this is the equilibrium equation of polar coordinates in 2D. Now we have a special case, axisymmetry, which I will be discussing very shortly. Now coming into the core part of the question is to derive the equation of equilibrium for axisymmetry. So what is axisymmetry? Axisymmetry means the body is symmetric about z axis. The z axis is called axis of symmetry. Now if you take a cylinder, the axis is through the center of the cylinder, and this axis is oriented, let us assume it is along the z direction. So about the z axis, the entire structure is symmetric. So a cylinder is an example for an axisymmetric problem. So whenever you are asked what is axisymmetry, you have to explain with 2 points. Stress components are independent of theta, that is dou by dou theta equal to 0, and deformations are symmetric about z axis, which means the shear components of stress in the theta direction, that is tau r theta equal to tau z theta equal to 0, and the boundary conditions, solutions, everything are independent of theta. So if you are asked what is an axisymmetric problem, you should at least write 3 important points. Body is symmetric about z axis, dou by dou theta equal to 0, tau r theta equal to tau z theta equal to 0. If you write these 3 points, you will get 5 marks. So now let us apply these 2 conditions, that is dou by dou theta equal to 0 and tau r theta equal to tau z theta equal to 0 in the equations of equilibrium. So for axisymmetric problem, dou by dou theta equal to 0, tau r theta equal to tau z theta equal to 0. So we will get sigma fr and sigma fz. So here the equilibrium equation about the theta direction will completely vanish. Why? Because the stress components are independent of theta, dou by dou theta equal to 0. So if we apply the dou by dou theta equal to 0 and tau r theta equal to tau z theta equal to 0 in equations 1 and 2, Equation 3 will completely vanish. In equations 1 and 2, we will get these equations. You can mark Br equal to 0 as body force equal to 0, Bz equal to 0 as body force equal to 0. We will get dou by dou r sigma rr plus dou by dou z to rz plus sigma r minus sigma theta by r equal to 0. Similarly, sigma fz equal to 0 gives dou by dou r to rz plus dou by dou z sigma zz plus dou rz by r equal to 0. Now, what you need to take care is that there are three equilibrium equations, general equations. If you are asked to write the equilibrium equation in 2 dimensions, you have to neglect the z axis and the stress components in z axis, as I have explained earlier, and you have to write these 2 equations. Now, axisymmetry is a special case of 2D, that is not a general case of 2D, it is a special case of 2D in which dou by dou theta equal to 0 and tau r theta equal to tau z theta equal to 0, and you have to apply the equations in the 3 general equations, so that the equation along the theta direction will vanish and you will get the equation along r direction and z direction only. So, we have already discussed the equilibrium equations in 2 dimensions, that is we are neglecting the z axis and the corresponding z components to get 2 equilibrium equations in 2D. Remember, axisymmetry is another special condition. Even though it is a 2D, that is a special case of 2D. If you are asked the general 2D condition of polar equilibrium, you have to neglect z axis and you have to arrive at this equation. Now, these are the basic equations in polar system which you need to by heart. So, strain displacement relation epsilon rr is equal to dou by dou r of ur. What is ur? It is the displacement in the radial direction. Now, what is epsilon theta theta? ur by r plus 1 by r dou by dou theta u theta. It is the displacement in theta direction. Now, this is the normal strain in the theta direction. Now, what is gamma r theta? 1 by r dou by dou theta of ur plus dou by dou r u theta minus u theta by r. What is Hooke's law? So, Hooke's law constitutive equation, we have 6 equations similar to that in XYZ system. You can see here what is epsilon rr, 1 by capital E into sigma rr minus nu into sigma theta theta plus sigma zz. Similarly, we can obtain equation for epsilon theta theta and epsilon zz. Now, what is gamma r theta? Gamma r theta equal to tau r theta by g. So, mostly in cylindrical system you will be asked for 2D cases only, not 3D cases. Now, what is Airy's stress function here? Now, in XYZ coordinate system you might be remembering we need to check del raised to 4 phi equal to 0. If del raised to 4 phi equal to 0, it is a stress function, then we have to find out sigma xx, sigma yy and tau xy. So, in r theta z system, so how do you know whether the given problem is an r theta z problem? The equation will contain variables r, theta or z. How to analyze if it is an XYZ system? The equations will contain x and y. So, Airy's function basically contains 2-dimensional variables only. So, it will not be dealing with the 3-dimensional variables. So, here for Airy's function in r theta z, you have to check del raised to 4 phi equal to 0. So, what is the equation for del raised to phi here? Dou square by dou r square plus 1 by r dou by dou r plus 1 by r square dou square by dou theta square into this term. So, if you analyze this term, you can understand that if you multiply by phi every term in this part, you will get this part. So, you can see here dou square phi by dou r square, 1 by r dou phi by dou r, 1 by r square dou square phi by dou theta square. So, this is the way to remember the equation. If that you obtain 0, that means it is a stress function. If that is a stress function, if yes, what are the stress components? The stress components are sigma rr, sigma theta theta and tau r theta. So, how to remember these equations? Sigma rr is equal to 1 by r dou phi by dou r plus 1 by r square dou square phi by dou theta square, which is the term 2 and term 3 of this equation, this part. Now, what is sigma theta theta? It is dou square phi by dou r square. Now, tau r theta, you have to remember the equation minus 1 by r dou square phi by dou r dou theta plus 1 by r square dou phi by dou theta. Now, we shall discuss the derivation of Lamy's problem, that is the thick cylinder subjected to internal and external pressures. So, for familiarization of the components, I have written the stress matrix here. Now, this is the cross section of a thick cylinder in which you are applying an internal pressure here and it is parallelly subjected to an external pressure here. So, I have drawn another view in which internal pressure is shown and external pressure is shown, and this radius, the internal radius is Ri and external radius is Ro. So, you will be asked to solve for the thick cylinder problem for mostly a plane stress case, As I have discussed earlier, the cylinder is a case of axisymmetry, which means tau r theta equal to tau z theta equal to 0. Also dou by dou theta equal to 0, which I have not mentioned here. Now plane stress means sigma zz tau r z equal to 0. So if I apply these conditions on this stress matrix, the remaining components I am obtaining only sigma rr and sigma theta theta. So for Lami's problem, we have the equations for sigma rr and sigma theta theta. So this is how we are obtaining only two stress components, all other stress components vanish. So sigma rr is called radial stress and sigma theta theta is called hoop stress or circumferential stress. Now let us apply the equilibrium equation. As I have told you, we have three equilibrium equations. The equilibrium equation in theta direction vanishes because this is an axisymmetric problem. So dou by dou theta equal to 0, tau r theta equal to tau z theta equal to 0. The equilibrium equation in z direction also vanishes because this is a plane stress problem. So remaining, I am having the equilibrium equation in r direction only, and again applying the conditions of axisymmetry and plane stress, I am getting dou by dou r sigma rr plus sigma rr minus sigma theta theta by r equal to 0. So now this is a differential equation which is depending upon r only. So I am changing this dou by dou r into d by dr. So d by dr of sigma rr, because the sigma rr depends on r alone. So d by dr of sigma rr plus sigma rr minus sigma theta theta by r equal to 0. I am multiplying the entire equation by r, which will give this equation. Now r d by dr sigma rr plus sigma rr. This initial two terms can be written as d by dr of r sigma rr. That is, how do I obtain this? If I differentiate by UV principle, first function into differential of second function plus second function into differential of first function. So if I differentiate this component d by dr of r sigma rr, I will get the initial two terms of this equation. Now minus sigma theta theta equal to 0. Now I am substituting y is equal to r sigma rr. So I can rewrite the equation as dy by dr minus sigma theta theta equal to 0. I am marking it as equation number 1. Now what are the strain displacement relations we have discussed? Epsilon rr is equal to dou u r by dou r, epsilon theta theta is equal to u r by r plus some term which you might be remembering if you have learned, but that term vanishes. Why? Because this is a case of axisymmetry. So dou by dou theta equal to 0. So remaining we are getting epsilon theta theta equal to u r by r only. So which means u r is equal to r epsilon theta theta. So which means epsilon r r is equal to dou by dou r of u r. So this u r I am substituting here. Remember, this is the standard procedure for solution of fixed cylinders and also for rotating discs also. So this procedure you need to learn properly. Now substitute for epsilon rr and epsilon theta theta by Hooke's law. So what is Hooke's law? Epsilon rr is equal to 1 by capital E into sigma rr minus nu into sigma theta theta plus sigma zz. Here sigma zz vanishes because it is a plane stress problem. So I have not written that, which is equal to dou by dou r of r into epsilon theta theta I am substituting, which I am rewriting in this form. So we have r sigma rr, we have substituted as y, and from equation 1 in the previous page, dy by dr is equal to sigma theta theta. So if I substitute and rearrange the equation, I will get y by r minus nu dy by dr is equal to dou by dou r of r dy by dr minus nu into y. So remember, y is not a simple variable, y is equal to r sigma rr. So if I differentiate this RHS again, I will get, so this is by UV principle, that is how I get r dou square y by dou r square plus dy by dr minus nu into dou by dou r of y. You should not write as 0 because y is a function of r. So you should write dy by dr. So why I am changing this dou to d? Because since it is depending on single variable only, I can change the partial differential into full differential. So I will get r d square y by dr square plus dy by dr minus y by r equal to 0. So this equation was obtained from the previous relation where we have equated the strains in terms of epsilon rr and epsilon theta theta, and by substituting Hooke's law equations. Now we will get a second order differential equation in y, and the solution of this second order differential equation is y is equal to C1 r plus C2 by r. So what is y? Y is r sigma rr. So, R sigma RR is equal to C1 R plus C2 by R. So, from that sigma RR is equal to C1 plus C2 by R square, or you can write A plus B by R square. What is sigma theta theta? From equation 1, sigma theta theta is dy by dr, which is will fetch you sigma theta theta is equal to C1 minus C2 by R square, or A minus B by R square. So, if you are not well versed with all these portions, no problem. So, what you can do is you can just equate the relations till previous page, and you can just write we will obtain a second differential equation, and by solution of the second differential equation will give sigma RR is equal to A plus B by R square, or C1 plus C2 by R square, sigma theta theta is equal to A minus B by R square. Now, applying the boundary conditions. Now, what are the boundary conditions? At R is equal to Ri. R is equal to Ri means inner cylinder. What is the pressure? Pressure is Pi, internal pressure. Why I am putting a minus sign? Because the pressure is compressive, it is not tensile. So, I am putting a negative sign. Now, at R is equal to Ro, that is the outer surface. What is sigma RR? It is minus Po. Why it is minus Po? Because again the pressure is compressive. Now, the most important point you have to remember is that the boundary conditions must always be applied on sigma RR only, not on sigma theta theta. So, remember once again, the boundary conditions must be applied on sigma RR alone, not on sigma theta theta. Whichever case, whether it is a case of thick walled cylinders or it is a case of rotating discs, the boundary conditions are always applied on sigma RR alone. And by substituting further in equations, no need to find out with the calculations and all. Anyway, these two equations you have to learn by heart. So, sigma RR, after further substitution and finding out the constants C1 or C2 or A or B, whichever way you like, sigma RR is equal to Pi Ri square minus Po Ro square by Ro square minus Ri square, minus of Pi minus Po by Ro square minus Ri square into Ro square Ri square by R square. So, if you remember a basic skeleton of the equation, you can see sigma RR, here there is a negative sign, and sigma theta theta, here it is a positive sign, rest all are same. So, only thing you can remember Pi Ri square minus Po Ro square. Anyway, in the denominator Ro square minus Ri square for both terms, minus of Pi minus Po into Ro square Ri square by R square. And similarly for sigma theta theta, only positive sign, here there is a negative sign. And UR means what is the displacement after the application of force. UR is equal to, here also there is a way to remember the equation. This term you have to remember 1 minus nu by E into first term. This first term is common, 1 minus nu by E into this term into R. This term you should not forget. You have to multiply by R for both the terms into R, plus 1 plus nu by E. This term also you have to remember. Now, the second term is common, Pi minus Po by Ro square minus Ri square into Ro square Ri square by R square. If I again multiply by R, as I have multiplied here, this R and this R square get cancelled to give denominator R alone. I hope you might have understood. This term you have to remember, then first term you have to write, multiply with a R, plus this term you have to remember, again the second term complete you can write, and again multiply by a R. So, R in the numerator and R square in the denominator will give a simple R in the denominator. So, this is how you should remember these three equations for solving the problem. Now, let us see two special cases. That is, the first case is internal pressure only is acting and external pressure is 0. That is, Pi is acting and Po equal to 0. Now, let us impose the boundary conditions. Now, here you can see Pi is acting here, there is no Po. Now, remember the boundary conditions must always be applied on sigma RR alone. So, at R is equal to Ri, R is equal to Ri means this surface. What is the pressure acting? This pressure is also acting in the radial direction. That is why we are imposing the boundary conditions on sigma RR, not on sigma theta theta. Pressure is acting in the radial direction. So, at R is equal to Ri, sigma RR must be minus Pi. Why I am putting the negative sign? Because this pressure is compressive. Now, at R is equal to Ro, this is the outer surface. What is sigma RR? There is no radial stress, so it is 0. Now, we have got the boundary conditions. Our general equation remains the same. That is for sigma RR, sigma theta theta and UR, which I have explained in the previous page. So, we can substitute and we can find out the values. So this diagram represents the distribution of sigma RR and sigma theta theta. So you can see we will be designing for sigma theta theta. So why we are designing for sigma theta theta? Because out of sigma RR and sigma theta theta, mostly sigma theta theta will be having the highest value for stress. So we are always curious to see what is the maximum value of sigma theta theta. So sigma theta theta is maximum at the inside surface. So for most of the cases, sigma theta theta is maximum at the inside surface, that is at R is equal to Ri. Now what is the expression for tau max? Tau max is equal to sigma theta minus sigma R divided by 2. So how do you obtain the value for sigma R and sigma theta theta? You have to substitute in the general equation and you have to substitute the corresponding conditions as we have obtained in the boundary condition. Now what is the stress distribution? The stress distribution, this represents that at R is equal to Rho. Now here this I have represented for sigma RR and this I have represented for sigma theta theta. Now at outer surface sigma RR equal to 0. Now at inner surface at R is equal to Ri, we will be having a negative value for sigma RR. Now that is why I have drawn this diagram to downwards and I am joining. Now this is the distribution of sigma RR. Now for sigma theta theta, now this is our reference line. The maximum value for sigma theta theta is at R is equal to Ri, that is at this point. Now at R is equal to Rho, it is not 0, it is having some value, that is why it is touching at this point. Now this distribution you need to learn. You have to understand here that tau is tau max at R is equal to Ri, that is at inner surface of the cylinder. So now let us discuss a university problem. So here a thick walled tube with an internal radius 12 centimeter is subjected to an internal pressure 200 megapascal. E and nu are given. Determine the optimum value of external radius if tau max is limited to 350 megapascal. So here how do you get tau max? Tau max is given as 350 megapascal. We have the equations for sigma theta theta and sigma RR. So if you subtract those two equations and if you apply, now this is a case of Pi acting alone and Po equal to 0. So you can substitute Po equal to 0 and if you subtract sigma theta theta minus sigma RR divided by 2, that equation may contain a term R in addition to Ri and Rho. So Ri is given, Rho is to be found out. Now there will be an ambiguity what to substitute for small letter r. So you have to understand that tau is equal to tau max at R is equal to Ri. Now the second part, determine the change in internal radius due to applied pressure. So we have a ready-made formula for finding out the displacement, radial displacement UR, which I have already discussed. Now determine the change in internal radius due to applied pressure. So the internal radius change is at R is equal to Ri because the pressure is acting at the inner surface. So you have to put the condition R is equal to Ri in that particular problem. So let us discuss the second special case where Pi is 0, internal pressure is 0 and external pressure only is acting. Now as I have mentioned earlier, let us impose the boundary conditions at R is equal to Ri. At R is equal to Ri means here. Is there any stress acting? No, the pressure only Po is acting here only, there is no internal pressure. So we are applying the radial stress is equal to 0 because pressure corresponds to radial stress. Now at R is equal to Rho means outer surface, what is sigma RR? It is minus Po. So minus Po we are giving, why? Because the stress is compressive. Now we can substitute and find out the values. Now sigma theta theta is maximum at the inner surface, that is at R is equal to Ri. Now here I have drawn the stress distribution. Now this is for sigma theta theta. Now if you substitute the values for sigma RR and sigma theta theta, you will get the both values as negative. That is why I have drawn the stress distribution to the downward side. Because since this is the reference line, whatever stresses we are drawing upwards is positive, downwards is negative. Now since both are negative, now sigma theta theta you can see the maximum value is at R is equal to Ri, that is here. I cannot say minimum value. At R is equal to Rho, that is outer surface, sigma theta theta is having some value, it is not 0, that is why it is joining here. Now for sigma RR you can see sigma RR varies from here to here. Now we shall learn some topics from the rotating disk portion. So rotating disk, the previous university question were asked what are the assumptions while proceeding for the rotating disk problem. So, the assumptions are the thickness of the disc is very much less compared to the radius of the disc. Now, this is the section of a rotating disc, that is the axis of the rotating disc is oriented along z direction. Now, it is rotating, the omega is the angular velocity. Now, what are the relevant assumptions? The assumptions are the thickness is very less compared to the radius. So, when the thickness is less, that means sigma rr and sigma theta theta do not vary with the thickness, that is second assumption. Now, I am not explaining again why only sigma rr and sigma theta theta, because we are considering axisymmetry and we are considering plane stress case, so that final stress components will be sigma rr and sigma theta theta. Now, here axis of rotation is z axis, we are considering sigma zz equal to 0, that is stresses along the axis of rotation sigma zz equal to 0. Now, till now we were considering in all the cases the body forces as 0, as you might be remembering Br, Bx, B theta etc. equal to 0. We never considered body forces. In the rotating disc portion, we have to consider body forces which is acting in the r direction, that is which is acting in the radial direction as rho omega square r. What is rho? The density of the material of the disc, omega is the angular velocity and r is the radius of the disc. The material is homogeneous, that is uniform composition. Now, let us see the equilibrium equation. So, equilibrium equation axisymmetry means dou by dou theta, that theta, the equilibrium equation along the theta direction will vanish. Now, we are considering the stresses along the z axis is equal to 0, and so the equilibrium equation along z axis also will vanish. So, equilibrium equation 1 only exists, and if we impose these conditions, we will get dou by dou r sigma rr plus sigma rr minus sigma theta theta by r plus rho omega square r equal to 0. Remember, for Lami's equation or for thick cylinder problems, we had equations only up to this equal to 0. The body forces we had taken 0 for Lami's problem, but here we are considering the body forces rho omega square r. So, the rest of the procedure is very similar to the thick cylinder problem. If you have learned it properly, this is very easy to understand. Now, I am rearranging this term. I am multiplying this by r, and by rearranging, if I multiply this by r, I will get rho omega square r square in the next equation. I am writing d by dr of r sigma rr minus sigma theta theta plus rho omega square r square equal to 0. Now, I am writing r sigma rr as y, which means sigma theta theta is equal to dy by dr plus rho omega square r square. Now, I am moving on to the strains. What is epsilon rr? Dou u r by dou r. What is epsilon theta theta? Epsilon theta theta is equal to u r by r plus some term which contains dou by dou theta term. Since this is an axisymmetric problem, epsilon theta theta equal to u r by r only, which means u r by r equal to epsilon theta theta, which implies u r is equal to r epsilon theta theta. So, epsilon rr is equal to dou by dou r of u r. I am substituting u r as r epsilon theta theta, and then I will get this term. Now, Hooke's law implies epsilon rr is having this equation and epsilon theta theta is having this equation. Now, I am equating these two terms. I will get 2 is equal to 3, that is this equation is equal to this equation. I will get 1 by e of this term is equal to 1 by e of this term. Now, this sigma theta theta should be substituted from here. Sigma theta theta is equal to dy by dr plus rho omega square r square. Now, we have equated equations 2 and 3, and we have substituted for sigma theta theta from equation 1. Now, I am not making it complicated, I am trying to make it simple. By further solving, we will obtain a second order differential equation in y, where y is equal to r sigma rr. So, if you are solving that differential equation, we will get the expression for sigma rr and sigma theta theta as mentioned here, which is c plus d by r square minus 3 plus nu by 8 into rho omega square r square, and sigma theta theta equal to c minus d by r square minus 1 plus 3 nu by 8 into rho omega square r square. These two equations you need to by heart, so as to proceed further for solving the special cases as well as for solving the problems from rotating disc. Now, c and d can be determined from the boundary conditions. Now, let us discuss case 1, where we are having a solid disc and no external forces are acting. So, solid disc, I have drawn the section of a solid disc. Now, the boundary condition for a solid disc is at r is equal to 0. At r is equal to 0. Remember, we are always imposing the boundary conditions on sigma rr and not on sigma theta theta. Now, let us see at r is equal to 0 what happens. Now, for sigma rr at r is equal to 0, if I apply r is equal to 0 here, this term becomes infinity. So, the radial stress cannot be infinity. So, in order to avoid this infinity, we have to give 0 for d, so that this term vanishes. So, at r is equal to 0, sigma r cannot be infinity, so which means we have to give the value 0 for d. Now, at r is equal to b, that is outer surface, r is equal to b, there is no external loading, which means sigma r is equal to 0. So, if we apply this condition, we will get the value for C as mentioned here. Now, maximum stress, what is the value for maximum stress? The maximum stress value is at center. You can substitute at center r is equal to 0. If I substitute r is equal to 0, this term and this term vanishes, the remaining term is C. Here also, if I substitute r is equal to 0, this term, anyway this d term is 0, so this term is already vanished, this term also vanishes, so sigma theta theta equal to C. So, maximum stress is at center, which is having the same value for sigma r max and sigma theta theta max, which is equal to C, which is equal to this value. Now, at r is equal to b, sigma r is equal to 0, which I have already explained earlier. The values for sigma theta theta can be found out accordingly by substituting the values for r. Now, this is the stress distribution, you can find out. Here, this is b, that is the radius of the disc. Now, what happens at r is equal to 0? This is r equal to 0. Here, we are having the maximum value sigma max, which is sigma theta theta max and sigma r maximum. Now, at r is equal to 0, sigma r equal to 0. This is the stress distribution of sigma r. Now, here at r is equal to b, sigma theta theta is having some value. That is why this point is joining here. Now, let us discuss case 2, in which a disc is having a central hole, which I have shown in the diagram here. Now, this is a disc in which there is a central hole of radius a and the radius of the disc is b. So, our assumption is there is no external loading, which means the boundary conditions we are applying at ri is equal to a, that is the inner radius at a, there is no load is acting here. So, which means sigma r equal to 0. Remember, the boundary conditions are always applied on sigma r, not on sigma theta theta, because the pressure is acting in the radial direction. And at r is equal to b, that is outer side, we are not giving any forces, which means sigma r equal to 0 there. So, by substituting this boundary condition, we will get the value for sigma r and sigma theta theta as shown here. So, this equation you need to memorize somehow or other, so as to do the problem. Let us not go into finding out the values of the constants c and d, better remember this equation. Now, what is the value of sigma r max? Now, sigma r max is at r is equal to root ab. So, how do we obtain that? D by dr of first derivative of sigma r equal to 0. If we differentiate this equation with respect to r and if equate to 0, we will get r is equal to root ab, that is the maximum value of sigma r. Now, what is the maximum value of sigma theta theta? As I have explained earlier, in all the cases, the maximum value of sigma theta theta will be on the inner surface, that is at r is equal to a. This is the inner surface. So, this is the stress distribution diagram in which sigma r is 0 at r is equal to a and r is equal to b, and the maximum value of sigma r is at r is equal to root ab. Now, what is the maximum value of sigma theta theta? It is at r is equal to a, that is why it is shown here. Now, at r is equal to b, sigma theta theta is not 0, it is having some value, that is why it is joining here.